Hi, my name is Jim, and I want to provide a walkthrough multi-sim example here. And this is important because circuit simulation is going to be an aspect of just about every course in the program. So that's one thing. Secondly is that if we are going to do PC layout, one elegant way of doing this is to build a circuit in Multisim and then transfer it to its sister program named Altiboard. And then the third comment I have is don't believe what you see in simulation. Always question it. Multisim is a very, very good program. It's very complicated, and sometimes it yields answers which are absolutely not correct. So if your theoretical and simulated are far off, then double check both. Just use common sense in this. So this is our Multisim workspace, and what I want to do is step through this and not overlook anything. And at the very top we see some standard Windows operations here, file edit and so forth. Some of these relate specifically to Multisim operation, and the same is true with the second line. And then in the third line is what we're seeing is our all-important parts that we're going to actually use to build a circuit. And by using a house hover over, it'll kind of tell you what these represent. So here we have a button that actually starts the simulation, and when that you're simulating, this will turn red to stop it. These guys here are voltage and current probes, and also something called a differential probe that when you attach these to your circuit, it tells you things like current and voltage and so forth. We're going to be doing that today. And then on the far right side of the screen, let me move this in a little bit, we have our virtual instruments. So let me pick out, I guess this is good, Agilent function generator. And if I click on this, as it actually opens up, and this is what an Agilent function generator of this model here actually looks like. So the cool part of this is we get to push the buttons, and we have to turn it on, of course. And our outputs on our simulation are these two lines here, and they represent respectively sync and output. We do not need a ground on this instrument. And that's one of the disturbing aspects of Multisim is a lot of the instruments do not need a ground. So when you get into hand wiring, you absolutely need a ground. And that just makes the wiring of the circuit in Multisim easier. So let me close this and I'll delete this guy. Here we go. And the first order of business here is to save my design. So I'm going to do File, Save As, and then you need to pick a folder or create a folder if you like of a reference here. I already have one set up. So I'll just manipulate to that. Now if you're in a lab situation and you want to save this, it's important that you save it to the right folder. And that is because if you do not, it will be scrubbed if they do an update. So the folder you need to save it to, and listen carefully to this, is C temporary, C temp. When you do that, it'll remain there for the rest of the semester, noting that anybody can look at your circuit, anybody can change your circuit, and anybody can delete your circuit. Here's the message. Back up to a flash. Don't get lost having to rebuild a circuit because you lost it. So I'm just going to name this example 1. And I got the .ms14 in there, the file name extension, and then save. So I'm all set up now, and as I build this I can go save it so I won't lose any intermediate steps. So the first order of business here is to put some voltage into our simulation. So I'm going to go over to the leftmost icon on the top. It says place source, and then I'll open that. And I see here I have a bunch of different families for different types of sources. Now in AC circuits you're going to be using signal voltage sources. and in electronics 1, control current sources and so forth. But what we're interested in right now is power sources, so I'm going to click that. AC power source, this is industrial electronics. We don't need that right now. DC power source is shown as a battery, and that's perfectly fine. So when you select this, you're going to see the symbol, and this is what's going to end up being placed on the schematic. So I'm going to click OK and place a battery symbol here. And it came back to this in case I want to place a second battery symbol, which I might be doing in electronics too when we deal with op amps, but right now don't need it, not going to do it. Click close. Oops, I shouldn't have done that. And one extra step here. I do need a ground. So a ground is a reference point like the frame of a car, and I'm going to put one of these on the schematic. Right here looks good, and then I have the option of adding more if I so choose. I choose not, only need one. Now I'm going to put some resistors in here, and what we're going to build is a very simple series parallel circuit to get a handle on what's going on. So this little device here is going to be our place basic, and opening it up is we see again a bunch of different stuff here. We have a couple different virtuals, and virtual means it's not real. We have switches, transformers, relays, sockets, resistors, capacitors, and so forth, electrolytic, variable resistors. And if I were building a circuit board, I would be wanting to use this resistor because it has a footprint, as we can see over here. Now, since we're not laying out a circuit board, I can come up to rated virtual, and this offers me some advantages. And I'm going to come down here, and we see a whole bunch of stuff again. I'm going to come down here to resistor rated, and we see the resistor symbol. Click OK and put one of these in our workspace, and I want two more. So I'll click OK again and OK again. And I have all the parts I need right now to build our simple circuit. Also note that the thumb wheel on your mouse controls the size of your workspace. So you can adjust that as necessary. I'm going to make this a little bit larger so we can kind of see it better. And to drag the parts around, just left click on them and put them where you want to. In this case, what I want to do without having to wire in a non-standard way is to change the orientation of the resistors. So that's easy enough to do. All we'll do is right click on it, and then what we see here is rotate by 90 degrees, either counterclockwise or clockwise. And with resistors it does not matter. With other parts like diodes and electrolytic capacitors with polarity, it matters a whole lot. So I'm just going to set this guy vertical and then do the same with this guy. So I'm in position to wire up the circuit right now. So to do this, I guess this looks pretty good. And if you're doing this for inclusion in a report, is you want to wire it cleanly. That is to say, without having any loops or unnecessary wires in it. So to do this, I'm going to set my mouse here. Let me make this a little bit bigger again. I'm going to set my mouse here, and I see it turns into a little target there, a bullseye. I'm going to left click it and come up over to this point, which lines up with the R1. I'm going to release my mouse button, press my mouse button back down, and come over here and then release the mouse button. Oops. And that's what I was referring to. I could, end up with some loopy-doos in here, which isn't exactly what I want to do. Matter of fact, I'm going to have to do this over to do it right, I guess. So let me do that. Let's see, release, come over, straight in, click, and done. Now you may have noticed it put a number on the screen. And this is a net name, and you may not see this, so let's get you set up. I have this turned on in my version at home. So we'll just go up to options here, and clicking on options will come down to sheet properties. Clicking on that is what you want to do is have the radio button under Net Names, Show All, Selected. Now, I think it comes out of reset without this being the case. So if you click this and then hit apply down here, I don't have it applied because I'm already in it, and then OK, is you should see the net name above it. And we'll explain what this is good for in a minute. Next, let me wire in my other two resistors here. Bullseye over to this guy, and I'm going to release the mouse here. Click them here. That's good. Now I have to come off of this point to pick up the third resistor, and I don't have anything really I can do that with. But what I can do is come up with this one, release, oops, there we go, release, and click, hold down, and then make the connection, and do notice you have a dot here. So if I were to wire something, and don't do this, I'm just kind of showing you, and I want to cross a line, and I'll make something really weird here for a minute. There's no connection at this point because there's no dot. So you have to specifically, by releasing and re-clicking the mouse button, set a point. This is simply a crossover on a line, or the wire if you will. It means nothing, so I'll select it and delete it with the keyboard. Now let's wire in this resistor, and this time I'm not going to click on corners. I'm going to go down here. I think that's a good place to start. Go across to my battery. Now I'm going to go up to make the connection on the negative terminal, and what you see is that the wire kind of follows. Now that doesn't look symmetrical, but I'm going to go with it anyway. Clicking that, and then if I select the wire, and you can see that my cursor turns into an arrow, I can pull it down wherever I want it, and it'll remain there. So suppose I'm in a situation where I need to, and let me build this kind of, come off a corner here. So what I can do is click in white space, and you typically won't have to do this. Sometimes I do, and that'll put a dot, and then you can come over here to set that, and then you can run this to where you're going to, and then we have our completed circuit. The last thing we have to do, and note that the net name for this is a wire, it's all connected together. This is all part of the same net, which is 3. Now I need to connect the ground in the circuit. Everything you want to simulate in Multisim has to have a ground, and that turns into net 0. 0 is always going to be the ground. Now I can move around my parts now, and what happens is the Multisim will rubber band it. So I can end up with a bunch of strange lines, but it'll still work. Now, since we've already named this, what good is it? And if we have a large circuit, say with 15 numbers in it, and I want to do some simulation using the plotter, I don't want to have to remember the numbers. So what I'm going to do in this case is name it something so I can easily find it. So I'm going to double left click on a wire, and this is telling me that the present net name is 2, and I'm going to rename that as V out. And there's nothing special about the name you pick, except it cannot be the name of another net. If it is, it'll prompt you and ask you, do you want to tie these two nets together? Sometimes you want to do that, sometimes not. Also, in your preferred net name, you cannot have any spaces. If you need to break apart some words, use the underscore character to do that. And then I'll come down here to apply, and then select OK. And then what I see is my node here, output connection if you will, is now labeled V out. And likewise, I'm going to click on the wire, and I guess I can use properties here. Net name 1, I'm going to name this VN. Apply, OK, all is good. So what you don't want to click on to change the net name is the actual name itself. It's the wire that's the actual net. And you can move these around as you see fit, as you can with the attributes of the various parts. Note when I do this, there's a line that connects the resistor to the attribute, the value here. so that if you have a cluster of resistors, by clicking on it and moving it a little bit, you can always see which one this links to. And the same is with the designation of the resistor too. So this came out of the library as R1. And if I wanted to change it to something else, I could certainly do that by double clicking it. Label, we see it R1, and as long as I don't name it anything that's already on the schematic like R2 or R3, I could make this, if I wanted to, like R internal for internal resistance, but we'll just leave it as R1 for the time being. So we have here now our components, and it's not likely that we're going to pull this stuff out of the library and have it be the right value. So what I'm going to do here is click on the source and the value of it's 12 volts, and suppose I want to make that 10 volts. So all I do is type in 10 here, select OK. No, not so good here. Guess I didn't get the 10. Got 19. Click OK, and then we see that that's 10 volts. So let's see, suppose that I want to change the value of this resistor to 3K. I'll click on the resistor, and there's the attribute, it's 1K. I'll just make that 3K. And notice that this is in ohms, so you have to put either 3000 in here, or you can use the prefixes, in this case 3K. Further, notice that the rating of this resistor is 1/4 watt. That means if I exceed this using a rated virtual part, I'll blow it up. Now, blowing it up in multisim is a good thing compared to blowing it up in a real circuit if I forgot to calculate the power. Clicking OK now turns this into 3K. Likewise, I'll change the values of R2 and R3. I'll make this guy say, I'll leave him at 1K. Yeah, that'll be good. And I want to make this resistor 1.5K, so I'll just stick that in there also. And these values have been determined in advance to give me a circuit outcome that I want to use to make things clear. Now, to analyze this theoretically, what I'd have to do would be take R2 in parallel with R3, come up with an equivalent resistor, put that in series with R1, and then use voltage divider to find V out. So let us start by actually using a DMM out of a virtual instrument to do that. Elegant multimeter. Here's our guy. And clicking on this, I actually open the model number of the multimeter that National Instruments included here. Now, this is kind of important. Notice that the symbol that you're actually going to wire into the circuit has 5 leads. Here are the leads, 5 of them. So when we wire this, we just have to follow this this outcome here of the way this is illustrated. And what I want to use is this lead because it's ground, and this lead because this is volt, ohms, and diodes, and that's an input. So I'm going to do that to measure the voltage across this. So I'm going to come out of my ground here. There's my bullseye. Oops, there he is. And come down to this point and go over and wire this into my ground. And then I want to come out of this right here and go over to my measurement point, which will be V out. Now notice I can connect this anywhere on any wire because it's all the same, connected by wires. So I'm pretty much set up with that, and I'd also like to measure the current flow, perhaps here. Now to do that, I'm going to have to pull out a second meter. Oops, wrong one. Let's see, Agilent multimeter, here we go. And it has the same symbol, obviously, to do that. And I'm going to have to shrink my screen a little bit here so I can fit everything on it. Put him down here. I want to move this guy over to this point, and now I'm going to open this up, and then I see another meter, which I'll stick right down here. Now to measure current, we're going to have to use the center button, center jack rather, and this guy that says I on it. And this is common sense from the standpoint of manufacturers, because if you're set up to measure current and you put it across the voltage source, since an ammeter is supposed to have zero internal resistance so it doesn't perturb the circuit, it'll do damage, which in the case of our meters will be to blow a fuse. Yesteryear you could destroy a meter. So I'm going to be using these two here, which would correspond to this wire and this wire. So to measure current, I have to put the ammeter in series with the circuit. So I'm going to click this wire and delete it. And notice that my VN also went away. And then I'm going to run the positive lead for the ammeter into my battery, and then the output will go to this lead, and I'm thinking that's looking pretty good. Now turning on the circuit here, we'll actually start the interactive simulation. And before I can see anything, well, it'd be nice to turn the power onto the meters. And this is presently set up for VAC, voltage AC, and well, we're not doing that. So I'm going to click on DC, and then what I see is 1.667 volts. And then over here, I'm going to turn this guy on. And what I need to do now is, this is coming out of the library as VAC again, is I want to measure the DC current. Now notice that the DC current, DCI, is above the actual key. So that means if I want to set that, I have to go to Shift and then click this button. And the Shift is lit up here. And what I'm saying here is that the current flowing into the circuit is 2.7 repeat milliamperes. Now if I did the theoreticals on this, I would have 3K, that would be this guy, in series with the parallel combination of these two resistors, which is 600 ohms, giving me our total of 3600 ohms, which when divided into 10 volts would give me 2.7 repeat milliamperes. And then using voltage divider with 600 ohms here is what I would see is I'd get 1.667. So it's 600 ohms here out of a total of 3,600 ohms, so you can see that that's going to be a lesser amount. So we've successfully determined what the voltage is using a couple of Agilent DMMs. And also note that the jacks on this are showing that it's actually plugged in the circuit. And over here we have these two guys, which are over here. So that's pretty cool. Now let's do one other thing. I want to stop the simulation here, and I'm going to remove these, and I'm going to use a voltage and current probe. So let me delete this guy and delete this guy also. Now I have to reestablish my wire here, and this is going to come in as a different net name 1 again. Let me move my 0 back. I like it to be in the middle, not that it matters. And I'll make this larger. There we go. So to find out these parameters, is what I can do is use voltage and current probes, which are located at the top here. So I'm going to left click and release the voltage probe, bring it down and connect it to this point, move him over there. I'm going to left click and release the current probe and bring him down over to here. And I'll move him in this direction, and what I want you to note here is the arrow. So I'll explain what happens in a minute when I reverse that. So running the simulation now with the probes, is we see that the current is 2.78 milliamperes and the voltage at this point is 1.67. That would be what we expect. So stopping the simulation for a minute, and I'm going to click on this. That's a right click, reverse the current probe direction, and simulate it again. And what I see now is the current is a negative 2.78 milliamperes. Now the reason it's negative is because the conventional current in the circuit is flowing this way, and we got the current probe in it saying that we're expecting a conventional current to flow in the other direction. So that's easy enough to fix, and you just have to be aware of that and know what the negative means if you pull one up. So the other thing I could do here, if I want to find the branch currents, that's simple enough, is to click on the ammeter, and I'll set him perhaps here. Oh, I didn't do that very well. I'll put him here and set the display here. Notice the line. Notice that the current is in the wrong direction again, so I'm just going to reverse probe direction. And I want to find the branch current here too. So I'm going to click the current again. And let's see, we'll set him up here. Let me get up at the top. Again, there we go. And my probe in this case again is the wrong direction, so I'm going to reverse him. Easy enough. Now notice that the last probe that I inserted here is in this leg. It doesn't matter if it's up here or here or here. It's in the same leg. And likewise, if I wanted to, I could put a current probe here, and that would display exactly the same value as this. Clicking on the run again is what I see is that the current through the 1K resistor is 1.67 mils, and the current through the 1.5K resistor is 1.11 mils. As expected, common sense, the current through this chain, this link, resistor rather, is less than this. If I add these two together, guess what I get? 2.78 milliamperes, which is Kirchhoff's current law. So more or less, I pretty much analyze this circuit by using meters and current probes. As you can see, it's not too bad to do this. So I guess the only thing I have left to do is to blow something up. So it sounds like it's going to be fun. So let me stop the simulation here, and I'll remove these probes. So to remove a probe, I'll just click it and delete. Click it and delete. Now there is one other thing that just came to mind. What if it asked you for the voltage across the 3K resistor? Well, you can take this voltage and subtract this voltage from it. Let me say that again. Take this voltage and subtract it from 10 volts. Now one way we could do that would be to put a voltage probe here, put a voltage probe here, run the circuit. This is obviously 10 volts connected here, 1.67 connected here. Doing the subtraction would give us the voltage drop across this, which would be about 8.3 volts. Or, let me remove this guy. This guy, I'm feeling like I don't want to subtract today, so I'm going to use what's called a differential probe, and that'd be this guy. So I'm going to bring him out. I'm going to set the first probe here, and then the second probe here. Now note the polarity on this, minus and plus. If I get it in backward, I'm going to get a negative. Running the circuit now is what I see is 8.33 volts across this resistor, which would give us what's left of that, 1.67 volts across these two resistors. So we've talked about three probes here, voltage, current, and differential probes, and I think it should impress you as being pretty cool for simulating circuitry. I'm going to delete this. Now to show kind of the nice part about, delete this too, using the virtual here is I'm going to do some damage in the circuit, and I'm not going to pay a whole lot of attention as to when I'm going to overload the resistor, and remember each one is rated for a 1/4 watt. So I'm just going to set this voltage for 1000 volts, and for sure that's got to do some damage. Click OK, and now I'm ready to simulate again, so I'm going to click this guy, and it's going to start our simulation, and wait a little second. Oh my goodness, it looks like we blew up all three resistors. So what we see here is Multisim blew the resistors opened, and that's typically what will happen in a circuit, is you'll burn the resistor up it'll form a high impedance path, meaning that it's not going to short anything out. So here, what this is telling me is my quarter watt rating for this is obviously not enough. I'd have to do the power calculations, that is 1,000 squared divided by the total resistance, which would be 3,600 ohms, to find the total power in the circuit, and then do that virtually using voltage divider to figure out the power rating of each resistor, and it's going to be much larger than a quarter watt. So that's what it looks like when this fails, and if you want to reset it again and change this back to a recent value, maybe I'll use I don't know, make it 20 volts. It's a nice number. Click OK, and I'm going to have to restart the simulation. So this is reading, the simulation is running. Any changes you make in the design will not take place until you restart the simulation. I'm okay with that. Turning it off, turning it on. See, the resistors are restored, and now if I take a voltage probe here, my expectation is that I should see double the voltage I had before, which I do, 3.33 repeat volts. So that'll conclude, and the nice thing about having this in video is you can start it and stop it anytime you want. Please work through this and become very familiar with Multisim, and then in the future here, what I'm going to do is build an AC Multisim walkthrough that uses a scope and a very cool tool named the grapher. So that'll conclude for now, and thank you for watching.